Today we're going to be talking about the derivatives of exponential and logarithm functions. Now, you don't go deriving these derivatives. You can derive them very similar to what we've been doing in the past using our definition of our derivative. So I'm just going to give you our derivatives of exponential functions. So the derivative of an exponential function where the base is some number and u is either a function or a variable, it's what your exponential function originally was, the ln of your base, and then the derivative of whatever is in the exponent. Now, because the ln of e is equal to 1, the derivative of e to the some exponent is just e to whatever that exponent is times 1, so we don't even write that, times the derivative of the exponent. Now derivatives of logarithm functions. The derivative of ln is 1 over u, and then the derivative of whatever, I call that inside the logarithm, so it's ever inside the logarithm. And then for a logarithm, some base other than e, it's 1 over whatever in the logarithm times the ln of the base of the logarithm times the derivative of whatever inside the logarithm, so du dx. And that's the chain rule. So these du dx's, that's our chain rule, how the chain rule applies here. So our first example, the first two examples really look very similar, but they're very different in taking the derivative. So what this is I should probably put in these parentheses so you guys understand that it's the ln of x squared. Now, what we can do here, there's really two ways to do it. I'm going to do method A, method B, and show you guys the differences between them. So method A, I'm just going to take the derivative as we normally would. So 1 over whatever inside the logarithm times the derivative of that x squared, which is 2x. So we simplify and we get 2 over x. Now the second way to do this is if we simplify first. Remember our rules of logarithms. You can bring down that exponent and put it in front. So we really have 2 ln x. So then I can take the derivative of that, and that's 2 over x. So we get the same thing either way. Now the second example, what this really is, this really means the ln of x, the whole thing squared. So here what we would do is it's a chain rule, so we'd bring down the 2 times the ln of x times by now the derivative of ln of x, which is 1 over x, so that goes in the bottom. So as you're doing your derivatives, you can be simplifying as you go along. So that's what our answer would be. Now, the next example, we have x times by log base 2 of x. So we have a product rule. So y prime is derivative of the first, which is 1. Leave the second alone. Plus, leaving the first alone, times by derivative of the second. Well, that is 1 over x ln of 2. Simplify. So y prime ends up being log base 2 of x plus 1 over ln of 2. Now, question number 4. I'm going to do this one like the first example, version B. what I'm going to do here is I'm going to say that this equals so now I can bring down the 1/2 in front. Now I can take our derivative from here. So y prime is equal to 1/2 times by 1 over x squared minus 4, what was ever inside our logarithm, times the ln of 5 times by now the derivative of the inside piece, which is 2x. Simplifying that or making it look a little bit nicer, we have 2x, 2 times the ln of 5 times x squared minus 4. A simplification we can do is cancel out the 2's, so that gets us x over ln of 5 times x squared minus 4. Number 5. Again, I'm going to use the properties of logarithms here. And I'm going to use a bunch of our properties of logarithms. 1/2 is like, or the root is like a power of 1/2, so I can bring that down in front. Now when I'm dividing, I can also break that out under subtraction. I'm going to distribute the 1/2 because the 1/2 is going to go with both terms. So now when I take my derivative, I have 1/2 times by 1 over what's inside our function, our logarithm function, times the ln of the base e, which is 1, minus, again, 1/2 x minus 1. 1 over what's inside the logarithm times the derivative of the inside, which is 1, so that's our derivative. Now some exponentials for us. Here, I can't simplify this at all, so y prime, but I do have a chain rule. So e to the root x, then I need to take the derivative of the root x, so that is 1/2 x to the negative 1/2. And I'm okay if you guys leave it like that. If you want to simplify it, what would we do? We'd have it, 2 would be on the bottom with a square root of x. And again, in calculus, it's okay if we have radicals in the bottom. That's not a huge issue for us really anymore. Number 7, remember, when you have a logarithm and an exponential, and they are the same base, you can pull down whatever in the exponent out in front. This is going to simplify to y equals pulling down the exponent x squared ln of e. Remember, ln of e is 1. So really, that whole equation simplifies to that. Y prime is equal to 2x. Always a fun trick for math teachers and the AP. Derivatives now of an exponential. Remember, it's essentially the function that we started with times the ln of the base times now the derivative of whatever the exponent was, so that's 2x minus 3. So that is what our derivative is. Now some applications. We have a line with a slope of m passes through the origin. So one of the points on our line is the origin and is tangent to this curve. What is the value of m? So we know tangent. So we know when this curve happens, we're going to have some line that's tangent to it. Our line is going to have the point 0, 0 on it. But it's also tangent to that curve, so it's going to have the point x ln of 3x. Because that's my x-coordinate. The y-coordinate is whatever that is. So the slope of this line, which is m, is equal to the y-coordinates being subtracted over the x-coordinates being subtracted. What else do we know about tangent? Derivative is tangent. So our derivative, which is 1 over 3x times 3, or 1 over x, is also equal to m. So therefore, since those both equal m, I set them equal to each other. I cross multiply. I get one side to be 0. You can't divide by x. That's assuming x can't be 0. So I set x equal to 0. We know x can't be 0 because we can't take the ln as 0. But I also set the other factor, ln of 3x minus 1 equal to 0. So ln of 3x equals 1. E to the first equals 3x. So x is going to be equal to e over 3. Now be careful here. We're looking for m, not x. Make sure you're answering the question. What is the value of m? We know that m is equal to 1 over x. So therefore, m is equal to the reciprocal of that, which is 3 over e. Our book, for some reason, is writing it like 3 times e to the negative 1. Okay, find the derivative and state the domain. So, finding the derivative. I go and I find the derivative 1 over 3x minus 5 times the derivative of the inside, so that's 3, so I should have a 3 on top. That's my derivative. And then I say, okay, my domain restriction on here, well, I can't have 0 in the bottom, so x cannot be equal to 5/3. Done, ready to move on. I approach this question very similar to what a lot of you guys would approach it, and to be honest, how I would have approached it when I was in high school. But remember, we can only take the derivative of values that were in our original function. So you need to also look at the domain restriction of the original function. Remember, ln, the inside piece of your logarithm, can't be negative. So the values of x that you're taking the derivative are those that are greater, where the inside piece is greater than 0, or x is greater than 5/3. So the domain of the derivative, you also have to look at domain restrictions of the original. So there's my derivative, and that is my domain restriction. Logarithmic differentiation. Logarithmic differentiation happens when we have a variable in the base and in the exponent. So we can't just take the derivative like we're used to. What we first have to do is we have to take the ln of both sides. So when I take the ln of both sides, I have the ln of y. And now because I've taken the ln and I have a power, I can bring down the exponent. So now what I do is I take the derivative like I'm used to. So 1 over y, but don't forget, that's implicit differentiation. Derivative of the first, leave the second alone. We have a product rule. Plus, leaving the first alone, derivative of the second. Now I need to take the derivative of x squared plus 1, so that's 2x squared, or 2x. And so since I had 2 x's, I multiplied and simplified all in one step. Now we solve for dy dx. So I multiply both sides by y. So I have the ln Now I need to substitute in what our y was. We substitute in what our original y was, which was x squared plus 1 to the x power. So that's how you do logarithmic differentiation, when you have an exponent or an x in your base and in the exponent. You can also do logarithmic differentiation when you have something of a complicated derivative. This is a super complicated derivative. But if I ln both sides, we have the ln of y, that 1/3 can come down and be a power. Now because we're dividing, we can also simplify that. Under subtraction, now I can go ahead and take my derivatives. 1 over y, we have an implicit there, dy dx, equals, well I know I'm going to have a 3x squared minus 1 on the bottom, times by the derivative of what was inside our logarithm, so that's 2x. I'm going to have something very similar over here. 3x squared plus 1 times the derivative of that, which is 2x. Now I multiply both sides by y. So I multiply by y. I multiply by y. I'm going to go ahead and then substitute in what y was. So I substitute in what y was. Y in our original equation was equal to this. And that's how you do logarithmic differentiation. Just kind of makes that derivative a little bit nicer. And also, if you think about it, we would have to do a quotient rule, and we try to avoid the quotient rule. That's all we have for today. Please make sure your lesson summary is submitted on time.